Hello, in this lesson, we would like to talk about a very important idea in calculus, which is to find the area underneath the curve, which leads to Riemann sum. So we're going to start with what is the area underneath the curve. In this case, we have a curve that is that's a parabola. It's between 0 and 1. The interval is between 0 to 1. And we want to know the area underneath the curve. Apparently, it is not exactly a triangle. It's a curly. One side is curly, the other two sides are straight. So we have to figure out a way to find an area underneath the curve as precise as possible. So the method we use here is a partition. So the first step we use here is a partition. Partition, in the case, in a simple example, say we partition the area into 4 equal parts. The equal parts meaning the horizontal partition is equal parts, right? So we have the interval from 0 to 1. So 0 to 1 is divided into 4 parts. And so in the interval of from 0 to 1/4, and from 1/4 to half, from half to 3/4, 3/4 to 1. So we divide it into 4 intervals. And these 4 intervals are 0, 1/4. The second interval is 1/4 to half. The third one is half to 3/4. And the last one is 3/4 to 1. Okay, on each one of this interval, okay, we are going to use a rectangle to approximate the area of the curve. For example, we're going to use this rectangle, this area, okay, which the height is the function value at the right endpoint, We're going to use this area to approximate the area of S1. And the second rectangle, we use the height. Okay, so let me mark the height. Okay, the height, which is going to be plugging in the function's value. Okay, I'm going to mark it. The function is x squared. So the height, right? So this height, okay, so this height, which is the height of a rectangle, I'm going to use a color, right? We're going to use the rectangle. So this height is going to be this much red. Oh, it doesn't show the color. Well, it shows a little bit, right? So how much is this height? This height is the value of the function at 1/4. And the second rectangle, I'll make a table for that, okay? So for each one of these rectangles, and we're going to choose the right endpoint and that function value. So this height, right, is going to be the function's value at 1/2. Okay, so I'm going to make a little table for you to show that. Okay, a little table, one more row. Okay. All right. So the first rectangle Okay, and that height is f of 1/4. F of 1/4 is plugging in 1/4 in the function, which is 1/4 squared. The second rectangle, we're going to use the right-hand side, the right endpoint to approximate, and that right endpoint is half. And that height is f of half equals to half squared. And that's so this is a rectangle, and that's the height of that rectangle. And the third rectangle, okay, is 1/2 to 3/4. And the height of that function, of that rectangle, is f of 3/4 equals to 3/4 squared. Okay, and the last one of these is from 3/4 to 1. 3/4 to 1. And that rectangle, which is the which is the fourth rectangle, S4 is approximated by the rectangle with height equals to 1, because that's the right endpoint, and that equals to 1 squared. Okay, to summarize, if you look at these four rectangles, right? If you look at these four rectangles, using the right endpoints to approximate, we can imagine that the total area under the rectangles is actually larger than the area underneath the curve. But we use it as approximation, okay? And so here I'm going to make the marking as our summary, and then we're going to calculate the area underneath the curve. Wait, there, okay? This is the interval. And that is the height of the rectangle. That's the height, okay? And what is the area of each rectangle? The area of each rectangle, oh, we have to talk about the width, right? The width of the rectangle. The width of each rectangle are the same because we have equal width, right? Equal width, which is 1 subtract 0 divided by 4, because we divide it into 4 parts. So the width is 1 minus 0 divided by 4 is 1/4. So the width is 1/4 for all of these 4 rectangles. And now, so they all have the same width. And what is the area? The area of these rectangles we have 4 such areas, right? So the area is going to be the height multiply the width, right? So the height multiply the width. Width is 1/4. Width is 1/4. And the second one is also the height multiply the width. We do this one by one. Multiply the height. Okay, the height multiply the width, which is 1/4. So the total area of the total approximated area is the sum of all these four rectangles, all of these four rectangles. So the approximated area we use right. Okay, so this letter is for right, meaning using the right hand side to approximate. And we also divide the entire interval into four pieces, so R4, and that is equal to the sum of all of these areas. Okay, the sum of the first area, and the sum of the second area, and the sum of the third area, and the sum of the fourth area. Okay, so that's the way of approximation. So that's one way of approximation. The other way of approximation is that we're going to use the left endpoint. Okay, we're going to use the left endpoint. That was the approximation. We use the left endpoint. But then you say, what if we use, we use the right endpoints, right? We use the right endpoints. Use the right endpoints. But then you say, what if we use the left endpoint? So we use these rectangles, right? You may see there's only three because we use the right endpoint. The left endpoint. The left endpoint on the first interval, the left endpoint is 0, right? So for the same table, okay, for the same table, for the same four intervals, okay, for the same four, so approximation using the left endpoint, okay, and the previous one is using the right hand point, right? So this is approximation using the right endpoint. And this one, what if we use the left endpoint? Well, if we use the left endpoint, the first rectangle actually is, we're going to use, I'm going to take this table and there will be changes. So what are these changes, right? If we use the left endpoint, and this is going to be the 0. It's 0 squared, right? The width, of course, is still quarter. And so the area is going to be 0 squared multiplied quarter. And the second one, we're going to use the left endpoint. So it's the quarter. So this is the left endpoint. That was the left endpoint. So this is going to be quarter squared. And that area is going to be a quarter. And using the left endpoint, so in this case, it's 1/2. Right? So this is a 1/2. That is the area approximating. So this is going to be 1/2. Using left endpoint here, so in this case, it's going to be f of 3/4. 3/4. Okay. So the result of this approximation, right? The approximation by left endpoints. So the first one we use, the first S1 we use 0 to approximate. The second one we use this one, the smaller rectangle to approximate. And the third one, we use this rectangle to approximate. The fourth one, we use this rectangle to approximate. So the area underneath the curve, okay, if we approximate using left side, left endpoint, it's going to be the sum of all of these. And you can see these kind of approximations. Sometimes we get an area larger than the actual area. Sometimes we get area which is smaller than the actual area. So if we keep doing this, right? If we keep doing this, whoops, sorry, this is a 3. This is 3/4. Okay, sorry. 3/4 is I'm adding this one to the total area using the left endpoints to approximate. So we're gonna get two numbers. Okay. This number, okay, this number is going to be, we can approximate, we can calculate it, okay, and that's approximately that much. And this one is going to be that much. They're very different as approximation. So the next idea is that what if we make the partition finer, right? So to make the partition finer, for example, we can divide into 8 subintervals. We can choose 8 subintervals. If we choose 8 subintervals, let's see, whoops. Okay, if we choose 8 subintervals, what are we getting? Okay, so if we choose 8 subintervals, we're getting, if we choose left endpoints or right endpoints, let's see what we're getting. Okay, so be patient with me. So on this interval, we're going to first have to know what are the endpoints. So we're going to have 8 intervals, right? So the width of the intervals is 1/8. So the first interval, okay, let me make this just a little bit smaller, okay? So the first interval is going to be 0 to 1/8. And that's the width of the interval. And the second one is going to be, the second one is going to be 1/8 to 2/8, right? So we're not going to reduce the interval. So, and then the third interval is from 2/8 to 3/8, right? So this interval right here from 0 to 1/8, 1/8 to 2/8, 2/8 to 3/8, 3/8 to 4/8, and so on and so forth, right? So I'm showing you these intervals. So 3/8 to 4/8, which is half, right? But we're not gonna reduce it. And 4/8 to 5/8, and 5/8 to 6/8, and 6/8. Oops, what am I doing? 6/8 to 7/8, and 7/8 to 8/8. 8/8, of course, is 1. Okay, so this is 0. So if on each interval, if we choose the left endpoint, right, we're going to use L of 8, L sub 8 equal to each area. If we choose the left endpoint, right? So for the first interval, the height is going to be f of 0 multiply the width of the rectangle, and which is going to be 1/8. The second one is we're going to choose the left endpoint, and that's going to be f 1/8 multiply the width, which is the height, which is the 1/8. We're going to have 8 terms. Okay, so let's be patient with me. And we're going to have f of the third interval is 2/8. That's the height. 2/8 multiply 1/8. Okay, we don't really need the dot. Okay, we don't really need the dot. And the fourth one is 1, 2, 3, 4 is f of 3/8. 3/8 multiply the width, which is 1/8. Plus, you can see the idea is the same. Is as we get finer, the sum becomes longer. Okay, so this time, let's see what we're getting. So the fifth, right? 1, 2, 3, 4, 5. The fifth one, 1, 2, 3, 4, 5. The left endpoint is 4/8. So that's the height of the rectangle, and the width is 1/8. We have 3 more to go. Okay, and the sixth one is f of 5/8, right? 5/8. 5/8 multiply the height, which is 1/8. 7/8, which is 6/8, right? The 7, that's going to be f of 6/8 multiply the width of 1/8 plus f of the last one, 7/8. 7/8 multiply the width. And these are the area. This is the area of the first rectangle, which is right here. The area of the second rectangle, which is right here. And that's the third one, which is right there, fourth, fifth, and until eighth. So we have 8 such subintervals. So if we plug in the number, okay, and f of 0, which is 0 squared, right? Because the function is x squared, right? The function is x squared, so we just plug in. So that's going to be 0 squared multiply 8. Okay, so I'm going to bring it over so we don't have to, let's do this. Okay, so 0 squared, 1/8, right? That's 1/8 squared. We plug in the function. And this one is going to be 2/8, that's going to be squared. And 3/8 squared, we're just plugging in the function. Okay. And we are going to get a sum. We are going to get a sum 5/8, and we're going to get a sum 6/8, and that's been squared. And the last one, 7/8, and we got the squared. Okay. Now, if we calculate, we're going to get a numerical value. We get a numerical value. Let's look at the right endpoints. The right endpoints, we also have 8 rectangles to approximate. But these 8 rectangles, we choose the right endpoints for the height of the rectangle, and they all have the same heights. Okay, so what we will have is that we're going to have 1/8 for the height, right? 2/8, 3/8. So we have all of these, okay? The right, for the first interval is 1/8. That's the height. That's the second height, right? The second height is right here on the right, and the third height. The third height is for the third rectangle is this one, and the fourth, fifth, sixth, seventh, and the last one is f of 8/8. Okay, and multiply the height. And if we plug in like we did last time, okay, if we plug in like we did last time, we will get, okay, we need to add the last one, which is 8/8, which is 1 squared, multiply 1/8. And we get another approximation from the right. And let's see what we get. You can see these two numbers are closer together, okay? In comparison with our partition into 4 subintervals, which these two results are so far apart, right? But each time these two numbers are getting closer and closer to the approximation. So this idea is to keep a partitioning into intervals that are finer and finer. In this case, we partition them into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So even finer. So we can work out some solutions as well. But this example is intended, what is it for n, right? So n, for the case of n, we're going to create some sums. We're going to show you just in a minute. So for 10, the right approximation is this number, right? And for 10, left approximation is the other number. So in comparison, okay, so let me make them just a bit easier to see both. So when we partition 10 times, the right endpoints give us 0.385, the left one give us 0.285, and you can see these two numbers are getting closer and closer. In the n equals to 50 case, they are like much, much closer, which means that we are getting closer and closer to the area, to the true area underneath the curve. So now let's look at how we're going to construct the nth case, right? How are we going to construct the nth case? So we're going to take this one, right? I'm going to take this one and we're going to construct the nth case. This is something we all need to learn how to construct, okay? So because now we have n subintervals, and from 0 to 1, this interval is divided into n subintervals. So the width of each subinterval is going to be, we're going to call it, okay, we're going to give it a special name. We're going to give it a special name, and this special name, we call it delta x. Okay, so I'm going to introduce this notation to you. Is called delta x. Let me see if I can find that delta. Right here, delta x. Okay, what is delta x equals to? The interval we divided into n subintervals is from 0 to 1. So 0, we call it a, b, we call it 1. So is b minus a divided by n. Okay, so I make the fonts a bit larger. So that's the width of the rectangle of the subinterval. In our case, it's just 1 over n. So let's look at each one of the subintervals. Okay, let's look at each one of the subintervals. Okay, this is actually, it's going to be an arithmetic sequence. Okay, it's going to be an arithmetic sequence. So we're going to show these subintervals as from 0 to 1 over n, right? The second subinterval is going to be 1 over n to 2 over n. And the third subinterval is going to be 2 over n to 3 over n. So this one, this example has, this convenience, right? So that's why we use this example, because it's made easier. And we keep going. Okay, we keep going. So what is the ith interval, right? This is the first one, second one, right? Third one. So what is the ith one? the ith interval is going to be like this. I minus 1 over n to I over n. We see this pattern from here, right? If the first interval is 1 over n on the right-hand side, so the ith interval will be I over n on the right side. So we keep going, and the nth one, right? The last one is going to be n minus 1 over n and the right endpoint is going to be, of course, n over n. So you can see the pattern. We didn't do any, we did not do any reduction. We didn't do any reduction. So if we look at the left, the sum from the left, okay, L sub n, right? So we take the left endpoint, left endpoint, left endpoint, left endpoint, left endpoint as the height of each rectangle. Then we will have, the first one is 0 squared, right? Or f of 0. Let me use f of 0 first, okay? Multiply the width. Right now, we're going to use the width as delta x because we're going to, this is going to lead us to a more generally formatted sum, okay? So the second one is going to be f of 1/n, okay? Multiply delta x, multiply delta x. So for each one of these rectangles, the width is delta x. We keep going, the first, second, third, so that's going to be f of 2 over n multiply delta x. And we keep going, right? We keep adding them until we add to the nth one, we take the left endpoint, okay? So that's f of n minus 1 over n and multiply delta x. So this is the area underneath the curve if we chosen the left endpoints. And what does that equal to? That will lead us to, right? That will lead us to, so first we're going to substitute all of these functions. F of 0, that's going to be 0 squared, right? And f of n minus 1, that's going to be 1 minus n squared. And this guy is going to be 2 over n squared. Then all the way up to this piece, n minus 1 squared. And how about delta x? Delta x is equals to 1 over n for all of them. So we substitute, and we just keep going, okay? Among all these terms, you want to see the general term, which is here, which we could, right? Which is going to be f, the left endpoints, right? That's I minus 1 multiply delta x. Multiply delta x. There we go. So in the middle, the ith term, right? The ith term would be I minus n, I minus 1 squared multiply 1 over n. Okay, so we have the ith term represented. And this is an algebraic expression. And what do we get? What do we get here? This piece, of course, is 0. okay? And all of these, we are going to get 1 over n squared. So they all have these denominators, right? And 1 over n is a common factor, right? We have 1 over n for each one of these terms. We're going to factor out the 1 over n. Okay, we'll factor out the 1 over n. And in the bracket, we have 1 over n squared. So we ended up with 1 squared over n squared. That's from the second term. The third term is 2 squared over n squared. It looks like we have a pattern here, right? And all the way we have I minus 1. So we keep adding them. Plus we have I minus 1. Okay, let me write it down this way. Okay, so I minus 1 squared over n squared. Okay, and the last term, of course, is this piece. And that piece can be written as n minus 1 squared over n squared. We obviously have a common denominator. If we use this common denominator and we combine, what do we have? So we have 1 over n outside, and we also have a 1 over n squared, right? We're going to factor that n squared outside. So inside the bracket, we have 1 squared plus 2 squared plus 3 squared plus all the way adding to n minus 1 squared. There. So this will be the approximated area if we approximate from the left endpoints. However, we know another fact, okay, that's what we learned in pre-calculus, okay? This fact is saying formula, this fact says 1 squared plus 2 squared plus all the way to n squared, okay, all the way to n squared, all the way to n squared. This is equals to n times n plus 1 multiply 2n plus 1 divided by 6. If we apply this formula to our situation inside the parentheses, but we have 1 squared plus 2 squared to, oh, sorry, this is supposed to be a squared. If we add all of these terms, there's n minus 1 term, and this is for n terms. So when we plug in the formula, we get on the outside of the denominator is 1 outside the parentheses n raised to the power 3. Inside, we're going to plug in this formula for n minus 1. So that formula, in this formula, everything will be changed. In other words, if we want to apply this formula for 1 squared plus 2 squared all the way to n minus 1 squared, we're going to have to make some changes. And that change is because we don't have this term, right? So this will become n minus 1. And this will be, n will be replaced by n minus 1. And this n will be replaced by n minus 1. And the result would be n minus 1 plus 1, that's going to be n, that's n, right? 2n minus 2 plus 1, so this part becomes 2n minus 1. 2n minus 1. So we're going to use this product. This is the sum for the whole of the parentheses. So we're going to take this guy and put it right here. Okay, so that's the final formula for if we divide the subinterval into n pieces. Okay, n subinterval. Use the left-hand side to approximate each one rectangle to approximate the total area, and that's the final we get. Okay, so we got a capital L of n equals to the whole of these. And the next question is that what if we take limit as for n approaches infinity? So this is when the limit kicks in. So we're going to take limit. Okay, not here, this one. So we take limit as n approaches infinity, right? On capital L left endpoint approximation, and we will get this limit. And how do we do this limit? And this is what we can do, okay? 6 can be taken outside, okay? We're gonna bring 6, bring 6 over here. N raised to the power 3, we're gonna bring it under here. Let me make the font larger, okay? Make the fonts larger. So we're gonna put n to the power 3 as n times 3, n times n times n, 3 times, okay? And this n, obviously, one of the n is going to reduce with the n on the top. And we're going to take this n divided into n minus 1. Let me show you. So we're going to rewrite it as 2n minus 1. And take this n outside. And n divide into each one. Okay, so let me write another line. So this limit, this term will turn into 1 subtracting 1 over n. It's just a simple algebraic manipulation. And this term is going to turn into 2 subtracting 1 over n. By this time, each has a limit. Each individual one has a limit. 1 over 6 is constant. So we can apply limit law. When we apply limit law, what do we get is that constant stays constant, right? And on this piece, we can take the limit inside. Okay, on that piece, we can take limit individually. That's what limit law told us we can do. So in the end, right, as n approaches infinity, 1 over n approaches 0. So we got a 1 over 6 times 2. So the limit is 1/3. So this is if we approximate using the left endpoints for each subinterval. What if we use the right endpoints, right? If we use the right endpoints and on these same subdivision, on the same division of intervals, and we will get the following. So right endpoints n subintervals equals to, right? So the first interval is going to be 1 over n is the height. Second interval, 2 over n is the height. 3 over n is the height. And the last one is n over n. So we're gonna have these areas, right? That's the first, second, and the last. And not the n minus 1, okay? The last one is f. I was just taking a shortcut, okay? So n over n, and multiply delta x. Multiply delta x. So let's check if it works, right? So this is for the first subinterval, this is the height, and that's the width. For the second subinterval, and this is the height, we use the right endpoints and multiply the width. And the ice one, we're going to use the right endpoint. So this is going to be I, right? And multiply the width. And the n minus one is this piece, right? There's one before this. And the nth one, this is the nth one. With that done, we're going to plug in, right? So when we plug in, I'm also going to steal this part, right? I'm going to steal this part for saving time. Okay, and of course this is the ice one, and we're missing the last one. The last one is going to be n over n. That's of course is 1 squared multiplied to x. In similar manner, 1 over n is equal to delta x in this case. And we're going to do same technique, the same algebraic manipulation, and we're going to factor out 1 over n. And we also factor out the n squared for each one, right? So we will get n raised to the power of 3. And inside the bracket, we're going to have 1 squared plus 2 squared, right? On this one, we'll get 2 squared. So we're actually going to get all of these plus n squared. Plus n squared. Okay? Now, in similar manner, okay, we're going to apply this formula, 1 squared plus 2 squared plus all the way to n squared. So we can directly use this formula to replace the bracket. Boom. And of course, we also have this 1 over n to the power 3. So that's the right endpoints approximation of each subinterval. And next, we're going to take limit. Okay, what kind of limit are we taking? We're going to take limit as n approaches infinity. Okay, on r sub n. R sub n, which is Rn. We're going to take the limit from right, which is equals to, we're going to take limit. It's going to be similar algebraic manipulation, right? And this n will take away one of the n under, so it's n squared under, and we're going to do similar manipulation algebraically so that we can apply limit law. So limit is here. 1 over 6 is put on the side, and for n squared, for n plus 1, we're going to split it into n plus 1 to 2n plus 1. So this is n, this is n. So once again, one more split, one more simplification. This part is turned into 1 plus 1 over n. And the next one is turned into 2 plus 1 over n. As n approaches infinity, each individual has a limit. Therefore, we can take a limit individually. And this will give us 1 over 6, okay? On these two, the limit can go inside. So this limit will go inside as n approaches infinity, and this is going to be 1 over 6 multiplied 2. It's a 1/3 once again. So this process from the beginning to this point, we have illustrated that these two limits give us the same area underneath the curve. The approximation from left using left endpoints or the approximation using the right endpoints in the limit state, we got the same limit. And this limit is defined. This limit is defined as the area under the curve, under this curve, and this curve, of course, is f of x equals to x squared. So recall the steps, right? Recall the steps. What do we have done, right? What do we have done? Is the first step, step 1, is a partition. Step 2, okay, the sum we've constructed is called a Riemann sum. Riemann sum. We had a, this is a Riemann sum. This is a Riemann sum. And that is also Riemann sum. And before that, we have L4, R8. All of these are Riemann sum. And so you can see Riemann sum can be constructed for the specific function that's given. Step 3, take limit. Limit can be taken as n approaches infinity, okay? Or sometimes we also take limit as delta x approaches 0. Same thing, because delta x and n has a relationship. Delta x approaches 0. Okay, so after all 3 steps is done, if we get a limit, and that limit exists, okay, and that limit will be defined as the area underneath the curve. Okay, so in our case, we found the area in the interval of 0, 1. So in general, right, we have a function, we divide it into n subintervals. For these n subintervals, we construct Riemann sum. How do we construct Riemann sum? We can choose the left endpoint or right endpoints, or choose a point in the middle, or we choose any point in the middle, right? Then the question is, if the limit exists, will they have the same limit? And we have proved theorem to demonstrate it doesn't matter which point we choose. If it's a continuous function, the limit always exists. Okay, after partition, after Riemann sum, for n approaching infinity, it doesn't matter which point we choose in each subinterval, left, right, anywhere in between. Okay, so all of these are examples of, constructing Riemann sum. And so when we choose left and see in these examples, we choose the points in between, right? It doesn't matter. You also don't have to be consistently choosing middle. You can choose left for one interval, choose right on the other interval. It wouldn't matter. Chosen point, we call it, for the ith interval, we call it xi star. Okay, look at this interval. This interval is become xi, x sub mi minus 1 xi. We chose this interval. Hold on. We chose this interval. Okay, I'm going to make some, I'm going to write something down here. Okay, a typical slice. Okay, that's what I'm calling it. The typical slice in this case, which is useful in the construction of Riemann sum, is that we are going to look at this interval, right? Look at this interval. This is a typical one. So this interval, and that's the width, right? That's how wide it is. It's delta x, right? And the height, we can choose any point in the subinterval. We call it a star, xi star. We use that xi star as our height of the function. So x sub I star. Okay, so that's the height. And multiply delta x, that's the width. So the height multiply delta x. So this is the area of a typical star. That area is the height multiply the width. That's f of xi star. So let me mark it over here. That's the height. Okay, that's the height. And the width, that's the width. Delta x. So this rectangle has a height and width, and the height is f of xi star, the width is delta x, from which we have constructed the area of a typical slice. Okay, so that's the typical slice. Okay, then we're gonna add them up. Okay, so imagine on the first area, we're gonna have f of x1 star, right? So for the first area, it's gonna be f of x1 star. Sorry about that. So I'm gonna rewrite it, okay? So the first one is x1 star plus the second one, which is of the second rectangle, is f of 2 star, right? All the way to the xi star. And all the way to the nth the nth rectangle. So this is the nth. So all of these, okay, we're going to use a notation. All of these means that the summation, okay, and from I equals to 1, this is the first one, right, all the way to n, and of f of xr. So we add them all up. So this is a summation notation. And that's our Riemann sum in general form. This is our Riemann sum in general form. Okay. So we got some definition from the textbook. Illustrate the same thing. Okay. And if this limit exists, right? So we have, you can see we have done the partition, x1 star, x2 star chosen, and that's a typical slice. This is a typical slice. We got Riemann sum. We'll take limit as Riemann sum. If this limit exists, and we're going to call it this the area underneath the curve, and we use that notation. Okay, we use that notation, and that notation is such. Okay, from A to B. Okay, on the interval, okay, f of x dx equals to that limit as, okay, bring the limit over here, and as n approaches infinity. So that's a definition of definite integral. You can see definite integral is to find the area underneath the curve between A and B on a specific interval. To construct such calculation, we're going to see some examples. And, you know, all these pictures. You also note sometimes the area can be negative. Area can be negative, positive, positive, negative. So in this case, there will be some, so in our calculation, there will be some cancellation taking place. Now, here's the theorem. If f is continuous, then even if there's a finite number of jump discontinuity, f is integrable, meaning that limit always exists under those circumstances. And this is the general formula you can use. Okay. This is basically to tell you to construct a Riemann sum and using the endpoints. You can see we use the endpoints. Xi is endpoints, right? And there's some useful formula which I use one of them over here. And this is the summation property. Okay, summation property. Because the integration, definite integral is defined based on integration, and these are the properties. If you add, for example, we're going to illustrate all of these, okay? What it means. The first one, okay, the first one means, I'm gonna explain to you what that means one by one, okay? The first one, summation notation, summation, right? I equals to 1 all the way to n. And there's a constant c. What does it mean? Is that for I equals to 1, we add a c. For I equals to 2, we add another c. For I equals to 3, we add another c. And all the way we're adding when I equals to n, and we're going to add another c. Okay, so obviously in this case it's n times c. Okay, if the second formula, meaning that also I runs from 1 to n, right? We have c times a sub I. What does that mean? It means that for I equals to 1, we have c times a sub 1. For I equals to 2, we have c times a sub 2. For I equals 3, we have a c times a sub 3. So we keep going all the way up to n. Okay, so adding them, the last one is C times A sub n. You can see that C can be factored out, right? After C is factored out, we will have A1 plus A2 plus A3 all the way. So that will be the sum of, that's why we have the second formula. Okay, the third one is that we have a summation. We have AI plus BI, B sub I. What does that mean is that for I equals to 1, right? For I equals to 1, we have A1 plus B1, right? And for I equals to 2, we have A2 plus B2 all the way to n, right? All the way from I to n, we get A sub n plus B sub n. And obviously we can regroup, right? We can bring all the A's together, all the B's together, and that's how we get, eventually, we get the sum to be separated, AI plus BI. For subtraction is the same thing. For subtraction is the same thing. So this is going to be, oh, let me just keep the A. Okay. So for subtraction, same. Okay. So if this is subtraction, all of these are going to be subtraction. And in the end, it's going to be subtraction. Okay. These other formula, you can just use them. You can just use them. Okay. You learn it in pre-calculus and you don't have to prove them again. We just use them. And because of these properties, the integration for definite integral, we only have addition rule and subtraction rule, and the constant multiply the integration rule. We don't have product rule nor quotient rule. Okay, by saying this, excuse me, I'm going to illustrate to you. Okay, I'm going to explain to you why this is, to understand this is so important. And over here, I'm bringing out the flashcards. Okay, and reshare our situation. Do we share that? Let's see, new share. All right. So on the flashcards, okay, let's go to the bottom of the flashcards, right? We got some properties here. These properties are on, the integration. These properties are on some of the integration. So I'm going to bring these properties over as this one. Okay. These properties, right? We have addition, subtraction. We have addition, subtraction. Okay, there should be subtraction. It's not listed there. Oh, there's subtraction. Subtraction is number 4. Okay, all of these properties, okay, they are actually inconsistency with the summation property. So I'm going to put this next to each other. It doesn't go up. There. We put these two properties next to each other. You can see, okay, because the definition of because of this definition, right? Because of this definition for definite integral. So when we lay these two next to each other, right? It's really the summation notation. It's really the summation notation is being used to define definite integral. So all of these properties, right? All of these properties is closely related to the summation properties. And that's why we don't have product rule nor quotient rule. Okay. Now, how do we express? Okay, how do we express? Let's choose a couple of the homework questions. Let's choose a couple of the homework questions to work with. Okay, so over here, you can see we just talk about a typical cell, a typical slice. For example, this one, the first one, the first set, right? From 17 to 20, we are asked to identify the function, express the limit as a definite integral. Take one of these, for example, right? Take 18. Okay, take 18, for example. Make the font a bit larger. Okay, so take number 18, for example. What do we have here is we got limits, right? We certainly got limits. And in the limit, right, f of x is being in the f of xi's place, we got x sub I, right, multiply the square root of 1 plus x sub I to the power 3, right? And delta x obviously is the width of the rectangle, and the interval is between 2 to 5. So what would be the proper expression? That proper expression, according to the definition, would be this. Equals to, right? From A to B, that's going to be 2 to 5. And what is the function? Well, this one gives the height, right? So the function would be x multiply square root of 1 plus x raised to the power 3. And delta x turn into dx. So that's how you work that question. Okay, on the second set actually requires quite a lot of work. Okay, the reason the second set requires quite a lot of work is because we're going to have to use the form of definition integration given the theorem to evaluate the interval. So we're going to do this, and I'm going to do number 25, and you can try the others. And so in this example, we're gonna see the work being done. Okay, so I'm going to bring the definition with us, and we're going to start working on the 3 major steps of constructing Riemann sum. Okay, so bear with me, and if you need to take a break, please don't hesitate. So our question here is going to be the integration, right? So we have the integration, and this integration is from 0 to 1. And the function is x raised to the power 3, x raised to the power 3 minus 3x squared dx. Okay, did I copy that correctly? There we go. Yes, I got it. All right. So we do something from scratch. And then when we partition, okay, so step 1 is partition. Partition the interval into n subintervals. Okay, so the width of the rectangle of the interval, right? So the width is going to be 1 over n. Okay, and we can borrow the interval we have partitioned before. Okay, so we've done something similar before, and which is this piece. So these are the n subintervals. We have n subintervals. So for each interval, but remember our function here is f of x equals to this piece. We can graph it, we don't have to, but for our visual effect, we let's just graph it. Okay, so the area we're looking for is between 0 to 1, so we can make some view adjustment, right? To right, and see what we get. Oops. That doesn't look very good. Let's see. So maybe -1 to 2. This is just so ugly. Okay. -1 to 7. All right. That's even more ugly. I think that's gonna make it a -8. There we go, right? We don't need the negative part, it's from 0 to 1, right? So from 0 to 1, let me make a little adjustment here, because you really don't need this picture. Okay, I put this picture here just to entertain. The view, the axes, 1, 1. So it's just from 0 to 1, right? From 0 to 1. Now I think I have a better idea as how to adjust it. So it's -5 to 5, right? This is from 0 to 1. Oh, this is just so ugly. Maybe set up to 2, and this is -4. Okay, so it's not a very pretty picture as I wished for, but it doesn't matter. Okay, so we can just not worry about that picture. Okay, normally you wouldn't need it because you know the function's height, right? So on each one of these intervals, so which point are we going to choose? Theory tells us we can choose any point we want. We can choose left endpoint, right endpoint, or even point in the middle, right? So for this particular example, I don't want to make it too long, so I'm going to choose the right endpoint. So for that right endpoint, and we know this is the interval, right? So we are going to have, we're going to construct for the first, so we're going to use R sub n, which is the right endpoint right? It's going to give us the same interval. So we're not going to do the left endpoint. We just do whatever is convenient because it's going to give us the same limit, right? So we're going to use the right endpoint f of 1 over n, right endpoint, excuse me, multiply the width, 1 over n, plus, right? The second interval, the right endpoint. So f 2 over n, and the width is 1 over n. The third one, right, is f of 3 over n, and multiply the width. So you know the drill, you know the drill. Plus, keep going until the nth one. The nth one, of course, is f of n over n, that's f of 1. Okay, I use n for n over n just for convenience, okay, and to show the pattern. But this time the function is different, okay? So this time the function is such. We have to remember that. Okay, so we're going to simplify. So f is going to be this function. It's going to be this function. And what we're going to have is that we're going to write it as a summation notation. Okay, so this is summation notation. All right. I'm going to borrow this form. We don't use limit yet. Okay, limit is removed. We haven't taken limit yet. F of x, you know, xi star, which is the right endpoint. So it's going to be this is going to be the I over n. I over n. Okay, you can use the notation just for convenience. So 1 over n. Okay, so that's it runs from 1 to n, right? It works, right? When I equals to 1 is f of 1 over n times the width. So that's the first term. When I equals to 2, we get the second. I equals 3, we get the third. I equals n, we get the nth. By using this notation, okay, so I'm going to show you. So why do I use this notation? Is there's some simplicity in there. I'm going to plug in the function f. This function is x raised to the power 3 minus 3xn. So when I substitute it by I over n, so x is substituted by I over n, and this piece is going to be I over n. And this piece is going to be I over n. Okay, see that? Okay, so this whole piece is f of I over n. So I put it here. That's f of I over n, multiply 1 over n. Okay, next I'm going to use some of the properties of summation. So I'm going to bring them closer to us. Okay, I'm going to bring them closer to us, which is right here. Okay, this one, I'm not going to delete it because it was useful for us, right? So I'm going to attach it to this piece for your notes taking, right? So that was useful. Okay, so I have these summation summation property next to me, so I'm going to use them. Next, right? For summation inside the summation, right? This 1 over n, I can bring them outside because it doesn't have anything to do with I, so I can bring it outside. Okay, so I'm going to bring this outside. Inside, okay, this will turn into 2 summation. Okay, subtraction, right? Look, the subtraction. So it could turn into two summations. That's what we're going to do. The next step, we're going to have 1 over n, and this is going to be a bracket, right? So these two pieces are going to be inside the bracket, and the summation notation will be separated. Boom. Okay, so this is separated. With this separation, 3 can be brought out. So I'm using the second property. 3 is brought outside. Okay. You guys need to learn the summation notation because you need it in calculus 2 as well. Okay. Equals to, let's see what we get inside, right? After this separation, and we bring the power, right? So this is going to be I raised to the power 3 over n raised to the power 3, right? And this piece is going to be I raised to the power of 2 over n squared. Okay? And next, we'll keep going. We will have 1 over n multiply inside the bracket. We can do the following, because n to the power 3, 1 over n to the power 3 can be taken out of the summation notation. Boom. And n squared can be taken out of this summation notation because it has nothing to do with I. Okay, so if you remove the denominator 1, this is I squared. And this is going to be I to the power 3. And what are these? Well, we just saw some formula right before this, right? So what are the formula? These formula are going to be useful for our case. Okay, so the formula is going to be useful for our case. How are we going to use them? Well, first we have to identify which one is useful to us, right? I raised to the power 3 added from 1 to n. So this third formula is going to apply here, and this second formula, so the sum of I squared is going to be applied here. So look, once we apply that formula, okay, in the bracket, this whole thing, we're going to put it inside here, and that piece, okay, will be replaced by this formula, which is n times n plus 1 over 2 and then squared. Okay, we just applied this formula faithfully. Okay, and of course you can write it differently, and this piece will be replaced by that one. That's going to be n times n plus 1 multiply 2n plus 1 divided by 6. Boom. So now we're getting ready to take limits. Before that, let's do some operations. So this squared is going to square the top and bottom. So this is going to be 4, and this is going to be n squared, and this is going to be n plus 1 squared. Next, let's do some reduction. We can remove the parentheses there. So this n squared, right? So let me write one more step. So this n squared is going to take away the n squared in the bottom. We have only n left. This n is going to take one of the n in the bottom, right? And what do we do next? We actually could bring the n inside. Bring the n inside. Bring the n inside. Of course, you can find common denominator, all that stuff, right? We're going to bring that inside and n plus 1 squared. We're going to distribute that n plus 1 to each. n plus 1 times n plus 1. The same trick. Okay, so 1 over 4, we keep it. And over here, this is 6, and this is 3. So we're going to bring the n. So we split these two. Okay, and bring one n here. And bring the other n here. Okay, we're doing the same trick. 6 and 3, so this will turn into 1/2. There we go. And one more step, right? Make them all, limit exist and as n approaches infinity, because as we're looking forward, so this piece, it turns into 1 plus 1 over n. And this other piece, is also, it doesn't matter, they're the same, okay? So it's 1 plus 1 over n, okay? And this piece, right, this piece is going to be the same. And that piece is almost the same, it's 2 plus 1 over n. Okay, of course you can do factorings or whatever, but this is good enough. So now let's take limits. So partition, and the second step, we done Riemann sum. We did it. I forgot to mark it. Step 2. Riemann sum. Right, so we constructed Riemann sum. Now we get to step 3. So Riemann sum. This time the Riemann sum is for Rn step 4 has 2 meanings, right? For our choice, we have chosen the right endpoint. And secondly is for Riemann, okay? So step 3, we're going to take limits. Okay, limits. All of these are not useful anymore. And we're taking limit, which is where is our limit notation? Our limit notation is right here. We just borrow that. Okay, and we're taking limit on capital Rn. Because that's the whole of the Riemann sum. Equals to, right, that limit on all of these we just found. There. Each individual limit exists. Each individual limit exists. So we can take limit individually. We can take limit individually. So these limits can be taken individually inside applying limit law. So in the end, what do we get? The first limit, this is 1. This is 1. So this is a 1, another 1. So this first part is a 1/4. Okay, subtracting. This makes 1 and this makes 2. 2 times half is 1, so minus 1. Oops. -1 should be placed here. So in the end, it's -3/4. So the total area underneath the curve is -3/4. Okay? Therefore, you can say this, right? This whole piece is equals to -3/4. Does it make sense? Well, remember we drew that curve at the beginning. It was an area underneath the curve. So we certainly have done, getting a negative number certainly makes sense, right? Certainly makes sense because we didn't have an area underneath the curve. And this area is between 0 to 1. So this piece of area is underneath the curve. So most likely we're right. Okay. That's the whole process and algebraic fun we can do with Riemann sum to find the area. In comparison, when we apply fundamental theorem of calculus part 2, which we can use to verify, is this answer correct, right? So we're going to use fundamental theorem of calculus part 2 to verify this. So we also learn to appreciate fundamental theorem of calculus part 2 because we don't have to do all of these summation. Okay, not to mention in many cases it's very difficult to do. Verify by fundamental theorem of calculus part 2. Okay, let's verify this. It's a definite integral. Okay, we probably don't need to do any substitution, anything. Okay, this is it should be pretty simple work. Just applying antiderivative. We know antiderivative, right? The antiderivative for x raised to the power 3 is 4/1/4. Whoops, what's going on here? Okay, so no, doesn't feel right. So 1/4 x raised to the power 4. Subtracting, okay, the antiderivative of 3x squared is going to be x raised to the power 3. Okay, because x squared is the antiderivative is the third of x raised to the power 3, so I omitted the other details. So with that, we're going to evaluate at 0 and 1, right? And what do we get? So this bracket, subtracting the other, it's the same bracket, but x substituted by 1. X is substituted by 1. And this x substituted by 0. So the latter part is all 0. And what do we get? I think we got, this is 1/4, subtract 1, and this whole thing is 0. So we get 1/4 subtract 1, that equals to -3/4. Yay, we got it right. Look how much work it took for us to use Riemann sum to approach to find the area underneath the curve versus just use fundamental theorem of calculus part 2, right? Huge difference. But that Riemann sum process is also important for us to understand, and you're going to need that for Calc 2 to construct 3D objects. Okay, that's all for this lesson. Thank you for watching.